So in Unit 5, lesson or notes 4, you're learning about how to draw covalent structures. And so I wanted to take a few minutes to create a video about the actual drawing part of the structures for those of you that might want to review it again. So we have to go back and talk about Lewis structures a little bit. This is about halfway through the notes. I believe it's like slide 7. And in Lewis structures, one of the things that's really important is that we use the element symbol to represent the actual atom itself. We use dots to represent the number of valence electrons that are present, and we're not talking about all of the electrons, we're just talking about the valence electrons. And then we use lines to represent bonds, and we also have to remember that one line is the equivalent of 2 electrons. So a dot is 1 electron, and a line is 2 electrons. Okay, so now we need to go and identify what's happening here between fluorine and hydrogen and chlorine. And when we do that, we're going to be we need to figure out the number of valence electrons. And you might recall from the past lesson where we had learned about the S block and the P block and the D block and the F block of the periodic table. And we also learned that elements, based on their electron configuration, so everything in the S block, if it ended in this column, its electron configuration would end with S1, which would make it have 1 valence electron. S2 would end with 2 valence electrons. And over here in this column, we would have things that end with their electron configuration with P1, but it would be a combination of S2 plus P1 for 3 valence electrons, S2 plus P2 for 4 valence electrons, S2 plus P3 for 5 valence electrons, S2 plus P4 for 6 valence electrons, S2 plus P5 for 7 valence electrons, and S2 plus P8 for 8 valence electrons. So as you go across the periodic table, everything in these columns have very specific numbers of electrons. And I said that we weren't going to focus on these for the time being. So going back to fluorine, if we look at fluorine here, we can identify that fluorine ends its electron configuration with S2P5, which means it has 7 valence electrons. So when I go down here, I'm going to draw dots to represent 7 valence electrons. So I have my 7 valence electrons, and I'm going to dot dots. 1, 2, 3, 4, 5, 6, and 7. And this one has 7 valence electrons as well. So 1, 2, 3, 4, 5, 6, and 7. Now, 7 plus 7 is equal to 14 total valence electrons. And that total number of valence electrons is going to be important when we finalize our structure. Now, because we're sharing electrons in a covalent bond, we need to show that the electrons are being shared. So the way that we do that is with those lines, and I kind of like to do a sloppy version of this first before I clean it up. So that tells me this loop right here tells me that this electron and this electron are the ones that are going to be shared. So when I rewrite this structure over here, I'm going to have my fluorine, and I'm going to have my fluorine, and I'm going to have this one purple line, and that one purple line represents 2 electrons. So then I'm going to go back and put these electrons that were back over here in. And once I've done that, I'm going to go back and I'm going to count a couple of things. The first thing I'm going to count is the number of electrons that I used. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I used all 14 of my valence electrons. The other thing that I want to count is I want to make sure that each atom has 8 valence electrons. So if I look at this atom on the right-hand side, it has 1, 2, 3, 4, 5, 6, 7, 8. And if I look at the atom on the left-hand side, it has 1, 2, 3, 4, 5, 6, 7, 8. So both atoms have 8 valence electrons. So this structure has created the most stable arrangement of valence electrons and lowered potential energy. Now, if we want to look at our next example here, we have hydrogen and chlorine. And again, I go back to my periodic table and I see that hydrogen is in the first column, so it has 1 valence electron. Chlorine is in the 17th column, and it has 7 valence electrons. So I have, for hydrogen, 1 valence electron, and chlorine has 7 valence electrons, and when I add them up, I get 8 total valence electrons. So I'm going to add my 1 valence electron to hydrogen and my 7 valence electrons to chlorine, like so. Because we know these are going to bond together, I'm going to loop them like this. Okay, and so then I'm going to clean up my structure and redraw it over here. So here I have hydrogen and I have chlorine, and I'm going to have my 1 bond in the middle, like so. And then I'm going to go ahead and add the electrons that I have. So I'm going to add the ones that were left on for chlorine, like this. And I'm going to remember that here's 1 electron and here's 1 electron. So if I count, I've used 1, 2, 3, 4, 5, 6, 7, 8 of my total electrons, which is good. And I want to make sure that every atom has 2. So I'm going to count chlorine first. 1, 2, 3, 4, 5, 6, 7, 8. It's good. It has 8 valence electrons. Hydrogen is one of the elements that we have to remember only needs 2 valence electrons to have its lowest stable arrangement of electrons. So 1, 2, so this is okay. So this structure works out the way that it is, and that's how we draw basic Lewis structures. Now, there's not every single atom or every single molecule that we're going to create has a single bond. Some atoms are going to create double bonds or triple bonds. And we learned about double bonds and triple bonds in the first semester when we were in our organic chemistry unit. We learned that every carbon-based structure that had single bonds would be considered an alkane, and every carbon-based structure that has at least a double bond would be considered an alkene, and every carbon-based structure that would be considered a triple bond would be considered an alkyne, right? Well, we didn't really talk about how multiple bonds form or why they form, so we're going to talk about that now. So a multiple bond occurs when there's not enough electrons to create an octet for all of the atoms present. So here we have oxygen, and if we look at oxygen on the periodic table, it falls in the column where there would be 6 valence electrons. So this one has 6 valence electrons, and this oxygen also has 6 valence electrons. And when I add those up, I get 12 total valence electrons. So when I draw this structure with oxygen, I have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So both atoms need 2 electrons, but I don't have any more electrons to give. I don't have extra valence electrons laying around. I only have 12. So what the atom will do is it will share a set of electrons twice. So here you might have this one, and here you might have this one. So in this case, if I'm looking at this structure, I would be able to note that there are 1, 2, 3, 4, 5, 6, 7, 8 electrons for the left oxygen, and 1, 2, 3, 4, 5, 6, 7, 8 electrons for the right oxygen. And if I look at it from this perspective, where it's just dots and not so much lines, I can see that there are 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. So both atoms have 8 valence electrons, but they can only achieve that by sharing 2 electrons or 2 sets of electrons. Then what I should also go back and count to make sure that I only use 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I only used 12 total electrons to achieve my stable arrangement of electrons. So that's how double bonds form. Well, not how, that's why double bonds form. And then we also have a triple bond, which we learned about earlier this year. And in our triple bond, it's sharing 3 pairs of electrons, and it usually only happens when there's a carbon or a nitrogen and sometimes an oxygen present, like individually. They all don't have to be there. So for example, nitrogen, according to the periodic table, has 5 valence electrons and 5 valence electrons, and when I add those together, I get 10 valence electrons to work with. So again, nitrogen is in this column right here on the periodic table, and we've already decided that it has 5 valence electrons. So what ends up happening in this situation is that we need nitrogen to get 8 valence electrons. So I'm going to create a bond here, I'm going to create a bond here, and I'm going to create a bond here. And so when I go and I look at it from this perspective, the nitrogen on the left has 1, 2, 3, 4, 5, 6, 7, 8 electrons, and the nitrogen on the right has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So this is the structure that usually gets drawn when we draw N2 like this. And what ends up happening is that, again, both atoms have 8 valence electrons, but we've only used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons total. Okay? Now the next slide in your notes, I ask you to draw Lewis structures based on elements in the periodic table. So we know So again, we go to the periodic table, we find out that nitrogen has 5 valence electrons, so we end up drawing it something like this. And now I'm going to draw this a little bit differently, but note that I didn't pair them up all the way around. I went 1, 2, 3, 4, and then 5, and I did that kind of on purpose. And I'm going to show again with magnesium how I'm going to draw these structures. Magnesium is over here, it has 2 valence electrons, so I'm just going to go top, and I'm going to go bottom, and that's it. I'm not going to pair them up. Bromine is over here, it has 7 valence electrons, and I'm going to go top, bottom, right, left, top, bottom, right. And see, I have that 1 valence electron left over. So that's one of the things that we're going to continue to like practice in that way. So let's take a look at how we draw the Lewis structure for water. We know that hydrogen has 1 valence electron and oxygen has 6 valence electrons. So in this case, I'm going to draw my I'm going to kind of keep track of all the electrons that I have. So for hydrogen, there is 1 valence electron, and in this chemical molecule or molecular formula here, there's 2 of them. So I'm going to multiply it times 2. And so that means that hydrogens are around for, or bring 2 total valence electrons. Oxygen, according to the periodic table, we said had 6 valence electrons, but there's only 1 of them, so we're going to multiply it times 1. So 6 valence electrons. So when I add this up, I have 8 total valence electrons to find a placement for. And so I'm going to start drawing the structure by just writing the elemental symbols. So H, O, and H. And then I'm going to add double bond, or just a single bond. So 1, 2. And remember, each line is worth 2 electrons, 2 valence electrons. So minus 2 valence electrons and minus 2 valence electrons. So when I add this up, 8 minus 2 leaves me with only 4 valence electrons to find a home for. And now I'm going to start placing those 2 valence electrons in pairs around atoms that need them still. So I'm going to put this one here and here, okay? Now, the reason why I didn't put one around hydrogen, a pair of electrons around hydrogen, is because hydrogen, as you might remember, only needs 2 valence electrons. So it gets that one from here, and that one from here, and here, and here. So now, both of these hydrogens have 2 valence electrons, and that's what they need. And oxygen has 1, 2, 3, 4, 5, 6, 7, 8, which is what it needs. So this is the correct way to draw the water structure. This is basically a list of steps that I follow when I drew water. So I'm gonna kind of talk through these steps as I draw the next couple of things. So we're gonna draw carbon and hydrogen, CH4. We're gonna draw this as methane. So I have carbon and I have hydrogen. According to my periodic table, carbon has 4 valence electrons and hydrogen has 1. So I'm going to take my carbon and say it has 4 valence electrons, and there's only 1 of them, so I'm going to multiply it by 1, which is going to give me 4 valence electrons. Hydrogen has 1 valence electron, but there's 4 of them, so I'm going to multiply it by 4, which gives me 4 valence electrons. And when I add all of that up, I get 8 valence electrons. Oh, we're running out of breath. Cool. So the first thing I'm going to do is I'm going to identify my central atom. And my central atom is usually the first atom that's presented to me in the problem as either, and as a symbol, or if carbon is present, it's usually carbon. So I'm going to put carbon right in the middle, and then I'm going to bond all of my other atoms to that central atom like this, with a single bond. Now, if a bond is equal to 2 electrons, and I've used 1, 2, 3, 4 of them, I was minus 2, minus 2, minus 2, minus 2, for a total of 8 of 0 electrons left over. So the question then is, did I use all 8 electrons? 1, 2, 3, 4, 5, 6, 7, 8, check. Are all of my atoms having 8 valence electrons? Carbon has 1, 2, 3, 4, 5, 6, 7, 8, yes. My hydrogens only need 2, so hydrogen has 1, 2, 1, 2, 1, 2, 1, 2, so this structure is drawn properly. We have another structure to draw. Maybe I didn't, okay, all right, well, so here, so we have carbon dioxide, CO2, right? So I have carbon and I have oxygen. And in this case, carbon, according to the periodic table, has 4 valence electrons, and oxygen, according to the periodic table, has 6 valence electrons. So carbon has 4 valence electrons and oxygen has 6 valence electrons, and they're going to be multiplied by the number of them. There's only 1 carbon present, that's 1. There's 2 oxygens present, times 2. So that's going to give me 4 valence electrons, and 2 times 6 is 12 valence electrons, and when I add that up, that is 16 valence electrons. Oh, I know what I missed, I forgot. So again, I'm going to start with the atom that's presented to me first, or carbon if it's present. And since carbon is present, I'm going to put my carbon in the middle, and to that I'm going to add my oxygens. And I'm going to try to put my oxygens as far apart from each other as I can. And so then I'm going to go start with my single bond right away. So I use 2 single bonds, so minus 2, and so 16 minus 2 is 14, minus 2 is 12, so that tells me that I have 12 valence electrons to find a home for. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now if I look at this, I see that oxygen here has 2, 4, 6, 8 electrons, carbon has 2, 4, 6 electrons, and oxygen has 2, 4, 6 electrons. And so I used 2, 4, 6, 8, 10, 12, 14, 16 electrons. So I used all of my electrons, but only one of my atoms is in a position where it has 8 valence electrons. So what I'm going to do is I'm going to use this opportunity to create a multiple bond. And I want to do it in a way that this oxygen will still have 8 valence electrons. So what I'm going to do is I'm just going to take one of these pairs of electrons and make it a bond here. And when I do that, if I clean this structure up as I go, oxygen now has 2 bonds, right? And it has 2 more sets of electrons, so oxygen has 2, 4, 6, 8, which is good. My carbon at this point still has this 1 bond here, but what I'm going to do now is I want both of my carbon and my oxygen here to have 8 valence electrons, and the only way to achieve that is through sharing. So I'm going to take this pair of electrons and make it a double bond here. And when I do that, and I leave the oxygen as it was, I now have 2, 4, 6, 8 for this oxygen, and 2, 4, 6, 8 for this carbon, and 2, 4, 6, 8 for this oxygen. And again, I still used all 16 of my electrons, so everything is working out here correctly, which is what we want. Now, there's one more slide that I forgot to print, I guess, and so I don't know what to do about that. If you need me to redo that one, we can. I'll add it as a separate video, but if you think this is good enough for your help for now, hopefully you feel more confident in drawing your Lewis structures for covalently bonded atoms.